Tanto io comunque sarei il secondo. Anche se se
vuoi acqua, prendi pure.
Solo capire dove sono i bagni. Mi butto a destra.
Sì, devi scendere le scale qua a destra e li trovi proprio sulla destra.
Ah, ok, devo scendere.
Sì, devi scendere. Non so dove siano qua in questo piano. Non ho ancora esplorato, però là sono, giù ci sono sì. Sì, da queste scale qua.
Good morning, everyone. We have some minutes to finish
Buongiorno, good
everything,
morning.
and then we can.
Eu não gosto. É prova de todos.
Prof, mi sta non la sentiamo da qua.
Mi sentite?
Guarda.
Potete darmi conferma che mi sentite?
No, vediamo che il microfono è acceso, però non sentiamo la voce. Cioè, vedo che sta parlando, ma non riesco a sentire pure qua il volume.
Mi
Sì, qua al
dispiace,
massimo.
proviamo a vedere.
Che non funziona. Tutto acceso.
Non so cosa dirvi. E ora mi sentite? Neanche adesso? Non riuscite a sentirmi?
Il share è connesso, però non sentiamo la... Non sento. Il volume è al massimo, il microfono è acceso, il suo...
Non si sente nulla, cioè ho provato...
Io vi sento bene nel sottofondo, ma voi non mi sentite, no? No, non sentiamo. Allora, il nostro funziona, infatti.
Cosa posso fare?
Provi ora?
Ora mi sentite?
No.
Però
Non so se ha delle cuffie, magari col microfono delle cuffie funziona meglio.
prendo delle cuffie.
Altrimenti... Non penso.
È l'unico che non sentiamo.
Io vi sento.
Sì, cioè, sì, anche perché gli altri non hanno...
Provato.
No.
Sentiamo scrivere.
Forse ora... Provi a parlare, però.
Sì, mi sentite ora?
Ora sì.
Mi sentite?
Moltissimo.
Bene, bene. Forte e chiaro.
Cioè, l'ho fatta?
Sì. Per fortuna.
Mi sentite?
Sì.
Sì, lei adesso...
Riuscite a sentirmi?
Sì,
Vi
adesso...
sento.
Hi, this is Lambros. Can you hear me? Hi. Good morning.
Ah, yes, we can hear you. Yes, we can hear you.
Yeah,
Hi.
this is Lambros. All right, cool.
Ok, thank you.
Perfect, thank you.
Ok, funziona tutto. Everything is working, so we can...
Funziona tutto. Allora, mi lasciate qualche minuto che recupero la mia presentazione e la sessione di oggi.
Certo.
Ce l'abbiamo fatta.
Ok, grazie.
Okay. Thank you so much. Just 5 minutes for organizing myself and the program for today.
Ok. Ci vede? Ciao.
Sì, sì, io vi vedo, vi sento, mi serve qualche minuto.
Ciao.
Sto organizzando.
Vedi?
Oh, ciao Chiara, sì.
Non mi chiamato Maria Chiara?
Ce l'abbiamo fatta.
Ce l'hai fatta?
Ce l'abbiamo fatta. Abbiamo avuto qualche difficoltà, ma adesso la stiamo risolvendo. Sono quasi pronto. Mi serve 2 minuti solo per organizzare e recuperare i file della presentazione.
Anche 3.
Grazie.
Is online and
The chair is online.
Okay. Everything running.
Yes, yes.
Okay, we can start. Thank you everyone for coming for this session. This is the section TISC IM1, section 4E. I'm Maroconi from University of Cagliari, and thank you everyone. Thank you to Sara and Chiara for our organization. We have 3 presentations. The first one is by myself and other authors. I present by myself. Then we have another presentation about circular management in the tunnel excavation and transport infrastructure and LCA approach. And then the last one is from Lambros Mitropoulos and Caterina Vouduri, Operationalization National Road Design Guidelines, a Python tool for geometric design, a consistent assessment. Thank you. I share my presentation with you. Okay. Someone can give me okay to. Can you see the presentation?
Yes, you can see the presentation.
Okay. The presentation that today we can look at the deep transformation. This is the story of reclaiming the sea by Cagliari, and how Cagliari, and this is an analysis, how Cagliari is turning in a 20th century urban fracture into a global model for Mediterranean sustainability. At the end of my presentation, let's step back in time to understand where is this journey begin. For decades, Cagliari has suffered from what we call the separation syndrome. Look at this image. The historical urban fabric, the texture rich with life, was completely disconnected from its most valuable asset, the maritime landscape. The sea was right there, yet completely out of reach. In the 19th century, Via Roma was a proud bourgeois saloon, but post-war reconstruction changed everything, prioritizing car over people. 20-vehicle lane became an invisible wall, a massive concrete barrier between the citizen and the water. You can see in this picture more than 20, 25 lane completely occupied by cars and private cars. This space, you can see a picture took myself in 2011, show the situation very clearly. As we look at the benchmark slide, it is vital to emphasize that Cagliari's master plan is not an isolated experiment. It's a part of a global trend. If you look at the grid in this slide, we have mapped out 7 global benchmarks. San Francisco demonstrates how removing elevated freeways healed coastal cities. Genova and Marsiglia provide that critical pedestrianization and dock conversion bring people back to the water. Thessaloniki and Auckland show us how linear park and multifunctional docks boost resilience. And finally, Oslo, Nice, Bordeaux provide an engineering blueprint for handling massive vehicular flow using declassification and intermodal rail integration. Cagliari's proposal synthesized all of this proven global lesson into a single cohesive Mediterranean model. And in this healing process in action, the new master plan started in 2011 in Cagliari administration and Port Authority that together are changing the perspective. This is a new blue and green space, a new vision. A space open for the people and restricted for the private cars, transforming asphalt surface and a congested transit hub into linear blue-green space. We are talking about 24,000 square meters of intervention, planting hundreds of new trees to mitigate the urban heat island effect and give the city back its lights. Also, to make room from the forest, traffic must be optimized. On the waterfront, we shift from restricted irregular lanes to 4 fully regular lanes. by eliminating lateral friction, and we achieved a smooth continuous flow, eliminating the classic stop-and-go effect. Beyond the target urban design intervention via Roma, far more strategic are the projects regarding the port, specifically the conclusion of new ro-ro and passenger terminal in the Porto Canale. You can see the aerial view and the part of waterfront, and the works in the north part of the new port permit to relocate some function, portable function, that have high impact in far from the city center in more easier accessible areas. Moreover, but a green space cannot survive without strong public transit. The new Arst light railway create a directed, seamless link from Piazza Matteotti and Piazza Repubblica, linking perfectly the main railway lines that arrive in the city, integrating urban and metropolitan networks in a single unified turf system. The work is under construction, and yesterday the first proof for the train was operating, and maybe the workers are expected to finish the next year. To handle high unbalanced flow, around the world there are a new approach for intersection to optimize pedestrian and traffic flow, the unconventional circular flow. This is not typical roundabout. In Italy, we have a very rigid regulation about roundabout. We have in Italy to have a perfect circular roundabout. It's an old specification, but there are unique specifications in Italy. But around the world, we have a dog-bone solution, like you can see in this picture. And another things that we are trying to implement in our vision, in our project that I show in the next picture, is the traffic evaporation. You can see the different scenario with the traffic light intersection and roundabout intersection. Maybe is like a traffic evaporation. Critics often fear the critics people often fear a car Armageddon when the car space is reduced. But this is the result. The data disapproves the meet bar Stockholm node. We unlock traffic evaporation, and of course, roundabout. This kind of circular flow for traffic improve safety, noise, air quality, energy impact. Pedestrian first is our goal. The core of the Cagliari Center, the waterfront, now is have a focus on the pedestrian experience, the pedestrian use, not limiting the traffic parasite. In this case, not also a project around the Cagliari, but also an important project for the new motorway around Cagliari, the Stata Road 554, are building to improve the connectivity between the east and ovest and the west coast, to avoid the transit traffic in our place. Finally, all of these things are implemented in a new vision. You can see the new nose with the unconventional roundabout circular system, and in this vision you can see the new port authority park green that are under construction. Partially is just open. obtained in the last April, last May, and you can see us during the work for Metropolitana of Cagliari, some circular system, in this case double roundabout, are building to prove the functional system. And this is the hand, it is a vision. This is a vision that we built for our city. In conclusion, Cagliari Waterfront is no longer just something you view quickly from the car windows. It is evolving to a resilient urban ecosystem, and we are proud to be part of this transformation. Thank you for your attention. I conclude my intervention. If I some question, I'm happy to answer. Thank you.
Thank you, Professor. I don't know if there are any questions from the audience. There are no questions?
No?
So, no,
We can.
Thank you.
No? Okay. Thank you so much. Now I'm put my jacket of the chairman, and I ask to the second presentation, maybe Daniele Sorraggi or Ilaria De Ponte, to share your presentation. Daniele, please can share your presentation and start to explain your work.
Yes. Do you see the presentation? Is in sharing?
Yes, yes, perfect. No, actually, I saw the image from the screen on your back. I see the room.
Now?
Okay, now it's okay. Yeah.
Okay. So today I share with you.
Okay.
Okay. Our research, circular management of tunnel excavation materials in transport infrastructure, an LCA approach. This is an evolution from my PhD thesis that from the meeting with the other professor from a Polytechnic of Turin, we developed an LSA approach to the management of soil materials. We start from a background analysis. The construction sector is now at a crossroad. It is responsible for more than a third of global emission and resource consumption in more. And the challenge of the TNT network is not only to connect Europe, but to do in a sustainable way. So about a third of the total waste product in European Union come from the construction sector and from the demolition activities. But the reuse rate of this material is less than 50%. So how can a construction sector implement a sustainable way to develop a new infrastructure? This study aims to fill the lack of literature on the application of the life cycle assessment methodology to the management of excavating soil and rock materials. In particular, it asks 3 research questions. First one, what are the real cost and benefit of reusing ESRs to renaturalize quarries? Second question, how does excavation technology influence this impact? And the last one, how can we quantify this management commitment from a life cycle perspective? We focus on renaturalization of quarries because when we talk about new transport infrastructure, we talk about a lot of amount of tons or cubic meters of materials So the first strategy implemented by the general contractor of this construction is to renaturalize the quarries. We start from a case study, the Terzo Valico dei Giovi. It is a high capacity rail link and part of the TNT Rhine-Alp corridor, which connects the port of Genoa with the Po Valley. It is more or less 55 kilometers of extension, and of this 55, 37 is underground. So the work produced about 15 million of cubic meters of material. So the main strategy found by the general contractor is not land filling, but circular use for the renaturalization of the used quarries. Actually, 78% of this material have a circular use, whose logistic depend on the construction method. The 22% is reuse inside the construction activity. But we focus on excavation technology. To realize this transport line, the general contractor uses two methods: traditional excavation with explosive and mechanized excavation. The materials that come from these two technical of the excavation have two logistic chain. The second one, the mechanized excavation, the faster, that use the TBM, have to do a temporary storage. So the materials with storage for eliminate the chemical additives that can permit the faster excavation by TBM. And then two different final destinations. This was quarry for a circularity of materials, and landfill that interrupt the circularity. We focus on only on the Piedmont section of this infrastructure, and we found four construction areas, sorry. COP7, COP20, COP5, and COP11. We selected four of them because two work with traditional excavation and two with mechanized excavation. And every of these construction site have come a final destination DP07, that is a quarry in Piedmont. So the material that come from COP7, COP20 goes first in DP22, a temporary storage, and then after some month go to the DP7. So we started with the methodology. So we try to develop the framework where LCA approach could work. First step, define the system boundaries. We focus on the literature module A5, the construction installation process, and we define only we isolate only the logistical and waste management phase. So we excluding the impact of the excavation operation. So we define two study scenario. One, material specific. We define material MA and material MB. Material MA come from traditional excavation, material MB come from mechanized excavation. So we have two logistic different approach. And then one system level. So we try to evaluate the impact of 1 ton of excavated soil and rock. Then we design the flow model of the LCA. So MA is material that transported directly to its final destination, quarry or landfill, and MD do the chemical additives used. It's required intermediate temporary storage, I already said. And then we try to find 3 KPI from the literature about LCA that could describe the impact of this management of materials. First, climate change, the total of greenhouse gas emission. Second one, the land use, the impact on soil resource and soil quality. And finally, abiotic resource depletion, fossil consumption of fossil energy. This is the flow of the flow chart of the 3 steps that we found to develop the LCA. The first, excavation of waste transport, that have 2 submodules, recycle and not recycle excavation waste. Second phase, excavation waste processing, have 4 submodules. Temporary deposit construction, because also the construction of the temporary deposit have a high impact. If we do only traditional excavation, we have not to realize the temporary deposit, so the temporary deposit have an impact to evaluate. Service road construction for the logistic of the temporary deposit. Waste managing activity inside the temporary deposit, and the recultivation activities of the quarries. Then the third phase is disposal of the non-recyclable excavation waste. We evaluate not only the real data come from the general contractor that 78% of material was recycled, but we define 3 different scenarios about the recycled materials. So the result from the first scenario, so the material base, we assess the environmental impact of 1 ton of excavation soil rock materials to be managed MA or MB. So MA from traditional, maybe from mechanized excavation technology. Isolating the effect of excavation technique and the environmental compatibility according to 3 waste scenario. W0, everything is recycled. W12, only 12% of materials go to landfill, and W78, the material is not chemical good, so every material come from the construction side go to the landfill, so no recycle. Focus on the 3 KPI. Climate change for MB has more 3 times higher impact than traditional excavation. From the RD fossil point of view, the consumption of fossil resource for TBM materials is 4 times higher than traditional materials. We see in the first part of the diagram and the third one. And then the land use for the material MA, the traditional, is impacting beneficial for the reneutralization of the quarry. On the contrary, for MB, the benefits is completely cancel about the construction cost of the temporary infrastructure. So we see the difference between this column of the diagram. And then result from the second scenario. For this case, we consider a fair distribution of material that occur 25% from each construction side, and we adopt a reuse rate of 22%. From this point of view, the transportation phase is the primary driver for the climate change and the fossil category, what we see in A5 1.1 and A5 1.2. The temporary infrastructure for the land use is the most impactful phase in the construction demolition of the temporary storage. And then the renaturalization, this activity makes a negative value. The third one in the diagram is really beneficial. The for the contribution of the land use indicator, and it reflects the restoration of original quarry landscape. So, in conclusion, circular management of excavation soil and rock is a clearly positive environmental transition for the territory, but is not climate-free. Landscape healing, reduction of the degradation and recovery of impacts through internal recycling, but by the other way, climate tax, a significant greenhouse gas emission due to the transportation and the construction of transit post for TBM excavation. So we try to find three answers to our research question. The principle of circularity fail if the distances are excessive. Optimize the transport route and preferring nearby quarries are the most climate efficient action for the general contractor. True, the use of TBM speeds up construction times, but complicated the supply chain of material reuse. So the environmental cost of a temporary storage must be calculated during the design stage to try to reduce them. And then third, tools such as LCA approach, LCA method should not be used as a retrospective reporting like this one, but to validate operation, but model to preventive optimization of for each site choice. So maybe that became a part of the project of infrastructure and not a solution to validate this impact. So conclusion, I'm here for question from the audience, the virtual audience, the meat and bones audience.
Thank you. Thank you, Daniele. Can you hear me? Yeah. And thank you. I don't have a question, but I have one consideration. I completely agree with you. The transportation is the main problem in the reusing this material for the sustainability. I work about this in this field because in my region we have a lot of amount of waste disposal. We are a land of quarries and mine. We have a lot of disposal around our region in Sardinia. The main problem is the transportation. And another problem is the waste regulation. Sometimes when we have the transportation project split in different sections, the best way is to disposal near to the next section. The material comes from another section, but the waste regulation prohibits that. It's incredible. There are a lot of problems because after 1 year, the material became not by product, it became waste, and there are completely different management. Thank you. Very interesting, your presentation. I don't know. There are another. Okay, have you a comment? You?
Okay. No, please. So we try to say, for example, we not write about that in this paper, but a problem is the different approach to law for the quarries. Every region has a different system to management that. For example, in this case, the Ligurian part of the project have a most simplified management for deposit as
okay.
The Piedmont one is most complicated. The general contractor for deposit excavation soil and rock in the quarries have to buy them. So the general contractor is now the most influent proprietor of quarries in Piedmont.
Of course. Thank you, Daniele. There are other question from the audience? Thank you, Daniele. We can move to the next presentation. Thank you so much. Very interesting, your presentation. The next one is Lambros Mitropoulos and Katerina Voudouria. I hope my pronunciation is right. And they present a work about geometric design consisting assessment Python tools to develop national road design guidelines.
Hello.
Okay.
Good morning, everyone.
Hello. Hi, Lambros.
You can
Please
hear
meet
me.
You.
You can see me, but I should share my
Yes,
presentation.
Yes, we can see. I can hear you. You can split. Okay, perfect.
You can see the presentation?
Yes.
Right. So,
please, the audience is yours.
All right. You can see the full screen right now?
Yes.
All right.
Yes.
Before starting, it's very impressive the regulation you just mentioned about your location that you cannot transfer, about transferring excavation material, and reuse it. Actually, I'm impressed. It's against circular economy. And so, my name is Lambros Mitropoulos. I'm assistant professor at the National Technical University of Athens in Greece. And today I'm going to present our work actually on roadway design and how we combine some existing guidelines. Nothing new about regulations, but we managed to do it a much better flow and for users in order to use it in their work. So this is a Python tool for geometric design consistency assessment. As we know, we have a big issue related to traffic accidents. 70% of fatal crashes occur on narrow, low-standard rural roads. And actually, we are talking here about undivided roads, which represent a very big share of the existing network in Greece and other regions around Europe. Actually, there is a high-risk context on these roads because often they are linked to unexpected geometry transitions. So we either have misalignments, we have curvature changes that are sudden, or the radius are very sharp, and we have very design shifts on overall. So geometric design consistency, as we are going to define it, and we have defined it in the literature, is essential for roadway design, roadway safety. And it's very important on rural two-lane roads, highways. So actually what is happening is the driver is surprised by the consistency of the attributes that are coming on the roadway, and they are not react in a way that is expected. So consistency is defined as the conformance of highway geometry to the driver expectancy. So the current limitation actually that drove us to work on this tool is that we have the national design guidelines. Actually in Greece, we rely on the German guidelines. We have adapted as it was like 10, 15 years ago. But however, we lack computational evaluation tools. The consistency is not systematically, though, addressed during planning, design, and safety evaluation. There are specific studies that are doing this thing. So the problem is that the assessments at the moment relies on manual subjective judgment, which leads to inconsistency. There are potential errors and no standardized decisions, however, therefore. But the thing is, like, as I told you, we have a guidelines, but in order to implement it, it's very difficult to follow the steps as these are not very clear within the guidelines, or there are misconceptions. And actually, due to the new technologies we have or designs, actually they lead to some decisions that are very, very not economic. So the objective here for us was to develop a Python-based tool that translates the Greek design guidelines into a reproducible method for assessing geometry design consistency. So here we focus on the horizontal alignment, which is composed of tangents and circular curves. The core metric we are using here is V85, the 85th percentile speed of the users on the road, to evaluate the consistency. And I'm going to explain how we are using this in the next slide. The limitations here, as I mentioned, is the excluding factors. Is we are not getting into vertical alignment, traffic condition, or driver behavior. So for this study, we are focusing on horizontal alignment. As I told you, designing consistency describes how well the road geometry matches driver expectations, reducing sudden maneuvers. The key components here are horizontal alignment, and we plan to expand it on vertical curves and intersections. So we have two criteria during assessing or auditing a roadway in Greece. The first one is criteria safety 1, which actually aligns the operating speed of a roadway with the design speed. So we would like the operating speed per each element of the roadway to be very close to the design speed. We were going to say how close. And this avoid large speed discrepancies. And the criterion number 2, which is speed continuity. Actually, here we assess V85 between roadway attributes which are successive. So this is tangent, curve, tangent, curve. But we have some specific here, let's say, differences that I'm going to elaborate a bit later. So all the two criteria ensure a smooth transition. The overall methodology, what we do in this Python tool here is very briefly, geometry extraction. We get a roadway which representing as tangent and circular curves. We take these elements, we separate the roadways on tangent and circular curves. We estimate the operating speed for each element based on the Greek guideline we have. We estimate V design, velocity design of velocity. And we then assess using criteria 1 and 2 in order to see the speed differences. And based on the speed differences, we assess each roadway element on a good, acceptable, or poor condition, which means we leave it as it is, or we have to do some minor changes, minor modifications, or we have to alter the whole roadway element. So going deeper into this Python tool, the horizontal alignment inputs here, we have, as we told, tangent and curve. So at the bottom, you can see for an example. So for a tangent, we have the length of a tangent with the total, it's again 8.2. We have the start of an alignment, the chain age, the end, and of course here we don't have a radius. But for a curve, we have 30 meters, which is the transition, the clothoid. We have the curve, the circular curve, 87 meters. Again, we have an outer transition, which is 30 meters, the clothoid, which is symmetric here we see. And we have the total length of the curve. And again, we continue the chain edge from 8.27. We add the L, the total length, and we have the end of the chain edge. And again, here, the radius of the curve is 135 meters. So this happens for all elements of the roadway. Either it is like 1,000 meters or going like 30, 40, 50 kilometers. So V85, I'm not going into details because this is special to every occasion, but to estimate V85, we are using kinematic relationships. We have different cases, and that's the first case only, just to mention what we take into account, and these are considered within the Python tool. For V85, for each element, we take into account the degree of curvature and the longitudinal grade. This is the only instance where we consider the grade of the road, because for these cases here, less than 5% or more than 5%, and this element length, we consider this relationship. Otherwise, we go to a different one. Everything is within the paper, though. And for the lane width of the roadway. So we have different relationships, and the Python assesses each time which relationship we are following, and for each roadway element considers V85. The difference here is we also have tangents, and tangents are considered as distinct design elements. So based on their characteristics, they are considered either as independent, partially dependent, or non-independent. Independent tangent is a tangent that is long enough for a driver to accelerate, get to stabilize the speed, decelerate again, and get to the next curve. So this means it has enough space to perform all these actions. If a tangent does not provide this space, it's a short one, it means that the driver does not have this space to accelerate and get to the next curve. So it's considered as not independent. When the tangent is independent, we consider it as an element, and we assess the tangent and the circular part of the roadway. Otherwise, we are moving and consider just the circular entities, and we omit the tangent between it. So it's not going into the assessment. So as I told you, we have two different criteria, and this falling within different categories. So when comparing V85 minus V design, we have, it can be good when the difference, the absolute difference is less than 10 kilometers per hour, acceptable 10 to 20, and poor more than 20. And again, for V85 between roadway element, adjacent roadway elements, as we mentioned, it has the same relationship. So for Greece, if we would like to improve something, the difference has to be, the final assessment has to be within 10 kilometers per hour. Or in some special cases, occasions has to be 10 to 15. So it's the upper bound. Everything else has to be changed, and we are going into different measures. So the Python we have selected, this Python selected, we have used Panda and NumPy. We integrated this tool. We have integrated, and we have an AutoCAD 3D alignment. We get into this, we give an order, we incorporate an auto list we have produced. Automatically, we extract the vertical alignment into a file. In the folder, we have the alignment. We copy-paste all the alignment elements from the platform of AutoCAD in an CSV file in the same folder. And we have developed an application, a Python-based application, where we give this just 2 files. Nothing else, nothing to do manually, nothing to copy, nothing to be prone in mistakes. So in order to test how these things work, we have a study location, which is in the southern part of Greece. Just for application reasons, this is 2.5 kilometers per hour. It's an undivided rural roadway. And it has been constructed based on older, let's say, guidelines. And there are a lot of accidents happening during summertime when this is much busier. So the road highlights real world constraints, and we went into it just to assess the first 2.5 kilometers of the roadway. Here are the results. As I told you, this is what produced from the tool. We get an Excel, which is, we can see all the formulas are dynamic inside. The Python actually splits tangent curves. It gives a coding. We characterize tangents. So if it is not independent, we do not address it. If it is partially independent or independent, it goes into the assessment. We adjust V85 just for these elements, which is based on the Greek guidelines. It's more complicated relationships. And we have the absolute values difference between criterion 1, V design minus V85. And we see here that most of them are good, and just one is happening to be acceptable within the range of 10 to 15 kilometers per hour. And we have criterion number 2, which see there are more actually elements that are in the acceptable, and they are more than 15 kilometers per hour. So we can see here that we assess R1 with tangent, the start number 1. So it assesses the subsequent R1 with tangent 1 T2, which is the next one, and goes as it follows. In the case that a tangent is not into the assessment, it skips the tangent and directly assess R3 and R4, curvature number 3 and curvature number 4. So actually, as I told you, these criteria main findings are most elements are in a good case. Criterion number 2 finds more critical locations that actually happen due to shortened tangent. So as an engineer, if I have this table, I know which sections are problematic, and we go exactly at this location to see what is happening specifically for each element, and actually propose new measures and new roadway design. Key contributions are we convert the Greek design guidelines, the safety criteria, into quantitative repeatable assessments, very easy to perform it automatically. We integrate this to this Python-based application, the CAD-based workflow. Everything has to perform manually, and we focus on the limitations here. We focus on, for the beginning, on horizontal alignment, and we exclude the vertical and driver behavior at this condition. So we bridge design guidelines and computational assessment here by this tool, and future works to integrate GIS, 3D geometric analysis, prediction models in order to bring inside more data that what is happening in the field, and actually use this tool into the alignment and expand it to intersection and roadway features in order to build safer roadway environment. And this concludes my presentation, and thank you very much for your attention.
Thank you so much, Mitropoulos, Professor Lambros. It's very interesting. I have a question. How old is the Greek regulation for the road?
How old?
Yeah, with the first regulation.
It has been drafted in 2001, and since 2000, which is accepted within the legislation, 2005.
2001, 2005, the same in Italy. The same in Italy. And we are, just a comment, we are experimenting the same problem because we need to integrate the new regulation for many things, many aspects. You point out your research, the consistency of the design, and in Italy a lot of professionals, also experts and the academy are put pressure to the minister to change the regulation to integrate with the new knowledge and new approach, new tools for the design. Your work is very nice. Thank you.
I agree with you.
Also the Italian example in the future.
I agree with you. The things should change gradually, and the guidelines, at least for Greece, is very short. It's not very iterative. And for civil design, civil 3D in AutoCAD, for example, that we teach in the universities, there is no kit in Greece. I know some countries, probably Italy has a kit, country kit, that they have used to check the design, or German kit. So in Greece, we don't have any kit like to integrate within AutoCAD. So everything is performed manually.
Yes, of course. Our regulation in 2000, 2001 was thought in the 80s, where the efficiency, capacity, velocity was the main guideline. Now we have to improve the people, the different approach, the sustainable mobility. There are we work in a different world, and we have to need to improve our regulation. Thank you so much, Lam. Thank you so much.
Thank you.
There are other questions.
No.
Okay, perfecto. Now, thank you everything for coming. Thank you for organization, and see you in the future. Thank you so much. Bye bye.
Thank you all. Thank you all for your time.
Bye.